You're looking at a screen right now, literally at this very second. But have you ever really stopped to think about the absolutely incredible journey that brought this image to you? Well, today we're going to pull back the curtain on the technology that powers our digital world. So let's dive in.
I mean, really think about it for a second. An image, full of color and life and motion, gets converted into an invisible signal. It's beamed through the air or shot down a cable at pretty much the speed of light, and then it's perfectly reassembled on your device. How is that even possible? Let's break it down step by step.
All right, so our journey doesn't start with the screen itself. Nope, it starts with a much bigger challenge, catching that invisible signal right out of the air, and it all begins with a very, very familiar sight.
Yeah, you've probably seen one of these on a roof somewhere. This is the Yagi-Uda antenna, and it is a masterpiece of simple, brilliant design. Each of those little rods has a very specific job. You've got the reflector at the back, the main element in the middle, and all those directors up front. They all work together to basically act like a telephoto lens, but for radio waves, zeroing in on a signal with incredible focus.
So, why is this design so good? Well, high gain means it boosts the signal, giving you a clearer picture even if the station is far away. High directivity means it tunes out interference and static from other directions. And that broad frequency coverage, that just means more channels for you to surf. It's just a super simple, super elegant solution to a really complex problem.
Okay, so we've caught the signal, we've got the data. Now for the next big question. How does your TV turn that invisible information into a vibrant, moving picture? Well, this is where the real magic starts to happen. To build an image from scratch, the TV needs two key sets of instructions. Think of it like a paint-by-numbers kit. First, it needs to know the structure, where to draw the lines. That's the resolution. And second, it needs to know what colors to paint with. That's the hue and saturation. You get those two things right, and suddenly you have a picture. Ever wonder why old TVs were so, well, squarish? That 4:3 aspect ratio was not an accident. It was designed that way for a reason. Turns out our eyes naturally find it way easier to track things moving side to side. Plus, it just so happened to match the shape of movie screens back in the day. It's a design choice that's literally rooted in our own biology. You know, here's a fascinating little secret. You're not actually watching a moving picture. What you're really watching is a series of still images, flashed on the screen so incredibly fast that your brain just blends them all together into smooth motion. It's a cool trick called persistence vision. But if the frames are too slow, you see that annoying flicker. And that's why your screen refreshes at least 50 times every single second to keep up the illusion. So whenever you hear tech specs like 1080p or 4K, this is what they're talking about. Vertical resolution is just the number of horizontal lines stacked on top of each other. And horizontal resolution is the number of tiny little picture elements, or pixels, on each one of those lines. The more lines and pixels you can pack in, the more detail you get. It's really that simple. All right, we've got the signal, and we have the blueprint for the image, but how does a flat piece of glass actually create light? To understand that, we need to go microscopic. We need to look at the wild evolution of the pixel itself. You know, this timeline shows a massive shift in thinking. We started with the brute force method of old CRT TVs, literally shooting beams of electrons at a screen to make it glow. Then we got clever with plasma displays, which were kind of like having millions of tiny controllable neon lights. And now, with things like QLED, we're manipulating physics at the nanoscale, using impossibly small crystals to produce perfect, pure color. If you were to slice a plasma screen open, this is what you'd see. It's basically this incredibly complex sandwich of glass, wires, and millions of tiny phosphor-coated cells. Each one of those cells is its own microscopic light bulb, just waiting for the signal to switch on. So how do you light up just one of those millions of tiny cells? Well, it's this awesome chain reaction. First, a jolt of electricity zaps a noble gas inside the cell, creating plasma. That plasma then emits invisible ultraviolet light. The UV light hits a special phosphor coating, and that phosphor glows, creating a single red, green, or blue subpixel. Now multiply that process by millions, happening thousands of times a second, and you get a bright, colorful picture. Amazing. But, of course, these days, our screens are fed by a lot more than just TV signals from an antenna, right? They're plugged into a global network, a digital superhighway that brings us everything from streaming movies to video calls with family across the world. The way the internet gets to your home is actually a really clever hybrid system. You've got these massive, super high-speed fiber optic cables doing the heavy lifting for long distances. But then, for that last mile into your house, it switches over to the good old coaxial cable that's probably already in your walls. It's the perfect combo of massive speed and existing infrastructure.
Sending data down a fiber optic cable is kind of like managing a massive superhighway. You need a traffic control system to make sure everything runs smoothly. And that's basically what SONET is. It's the set of rules that makes sure your movie, your neighbor's video call, and everyone else's data can all travel together at the speed of light without a single collision.
Let's break down the key players on this data highway. First, you've got the multiplexer. That's the on-ramp. It merges tons of different data streams into one single beam of light. Then you've got the regenerator. Think of that like a fueling station, boosting the light signal to keep it strong over hundreds of miles. And finally, the add-drop mux. That's your exit ramp, intelligently pulling your specific data off the main highway and sending it right to your home.
Okay, now for the final step. We're going to zoom in from that massive superhighway all the way down to the nanoscale. Because the physics that power our most advanced screens and networks, well, this is where things get really, really interesting. Okay, this is where things get seriously cool. A quantum dot is a man-made crystal so tiny it's only a few atoms across. And when things get that small, the weird rules of quantum physics take over. You shine a blue light on them and they glow with a perfect pure color. But here's the amazing part. If you make the dot just a little bit bigger, it glows red. Make it a little smaller, it glows green. By controlling their size with atomic precision, you can create the most vibrant, perfect colors imaginable. And this kind of quantum weirdness isn't just happening in your TV. It turns out the tiny components that create the super high-frequency microwave signals for all our wireless communications also rely on some very strange quantum effects. So, on the left, you're looking at a gun diode. It looks simple enough, right? Just a little piece of semiconductor material. It doesn't even have a PN junction like a normal diode. But then you look at its behavior on the right, and you see that it does something that seems to completely break the basic rules of electronics.
And here's the key. Normally, you put more voltage in, you get more current out. Simple. But with a gun diode, you reach a certain point where adding more voltage actually makes the current drop. This bizarre effect is called negative resistance, and it's this strange property that allows this tiny little component to oscillate and generate the incredibly high-frequency microwave signals that power our Wi-Fi, our Bluetooth, and our cell phone networks. You know, when you think about it, the evolution has been just incredible. We went from shooting electrons in a glass tube to engineering quantum crystals that glow based on their size. It really makes you wonder, what's next? Will our screens be holographic? Or maybe they'll be beamed directly into our eyes? The only thing we know for sure is that the magic is really just beginning.